We're continuing on with chapter 10 here. We're talking about energy. So last time we got into energy and some different aspects of it. A reminder that energy, there are several types of units that we commonly come across when we're dealing with energy. Common units are joules and kilojoules, also calories and kilocalories are very common units of energy. And remember that there's sort of a relationship between those two that they do want you to know. So, and it does come up a lot. 1 calorie is 4.184 joules. So that is definitely a conversion that we use a lot to go between the different units. And we'll use in this chapter as well when we do some specific heat type calculations. Overall, we kind of talked about the idea of two sort of energy processes. One is an exothermic reaction or process. And that is when heat and energy is released or basically given off. As we talked about last time, as we'll see today as well, there's kind of two symbols, I guess, if you will, for heat and energy that we very commonly come across. One is Q, which is for heat usually, and one is the delta H that we talked about, and that is the change in enthalpy. And the change in enthalpy is, again, really sort of the overall for a lot of reactions, how much heat or energy is either absorbed or released in those processes. And if we calculate either one of these, which we'll do in this chapter, and you end up with a value that is negative, that usually results or means that it is a exothermic process happening. So if you see the value of either Q given to you or delta H, and it is a negative value, regardless of really what the number is, the negative value is the one that's going to tell you it is a exothermic process overall, given off that energy. The other sort of process was endothermic. And that is when heat and energy is absorbed. And very similar, we do see a certain type of number when we calculate something like Q or delta H. These will result in positive values. So in pretty much all cases in chemistry, it's really important when you calculate energy, any type of energy, that you don't disregard sort of the sign. So the sign is really important in identifying sort of what is going on in that process, whether or not it is sort of overall sort of giving off the energy, which would be exothermic, or absorbing the energy. Sometimes people are taught like, forget about the sign, just, calculate the number or take the difference of temperatures and don't worry about final minus initials. So it's really, really important in chemistry to make sure that you do the calculation correctly and you keep the sign, because it does give you that important information. The other thing that we sort of talked about as well were some energy diagrams. We saw, we quickly sketched one here, our reactants and our products. And we also saw one that maybe looked like this, products and reactants. So these are energy diagrams where energy obviously would be on our Y here. And they both represent two different types of processes. Our first one here, we have our reactants that are lower in energy than our products. And whenever you have that situation, this is always an example of, that's actually both the same, huh? I drew two the same, at least I'm consistent, that's good. So here our reactants are lower in energy than our products. So always in this situation, and then one next to it that I drew the same, these are going to endothermic process. We need to put energy in there to get to our products. Let me actually draw the other one there. That'd be good. Thank you. Let's try. What was I going to do? I was going to do this move, I think. There we go. I just brought there. So in this one here, if we draw it correctly, we see our reactants are higher in energy than our products. So in order to get our reactants down there to our products in terms of energy, it's going to be an exothermic process, going to give off the energy to do so. We also talked about the hill that we see in this picture, and that is the activation energy. And for our exothermic, it would be this guy right here. And the activation energy is sometimes abbreviated of E of A, is that minimum amount of energy that's required for a reaction to basically take place. And as we talked about, it does have an effect on the overall rate of a reaction. So if you have a really big hill that the reactant's got to climb in terms of energy to get to the other side, it's most likely going to take a little bit longer for that to occur, as opposed to if you had a much smaller hill for everybody to climb to get to the other side, is going to probably occur faster. One way that we speed up a reaction is we add a catalyst. You sometimes maybe hear that. And what the catalyst does, again, is it lowers that activation energy hill, so it allows everybody to get over to the other side a lot quicker and a greater proportion of molecules to do so. We also see what we saw last time, that, the endothermic reaction typically has a larger hill, which makes sense since overall it's going to kind of need some energy to be put in there to help a good proportion of guys get to their side. Also, I think we looked at the end there, the difference between where the reactants start in energy and where they end in energy. That is the delta H of the reaction. So the difference there is the delta H of the reaction, which is basically found by taking the delta H of our products minus the delta H of our reactants. And we talked about state functions last time, that the idea that really the two most important things are where you start and where you end, not really your pathway to get there, but really where you start and where you end, and especially something like energy, that's important. And that's basically our products is where we end, and our reactants is where we start in a process. So in this one here, we see that the product number is higher than the reactant number. So when we subtract our product from our reactants in terms of energy, larger number minus smaller number will give us a positive value for delta H, which is what we would expect for endothermic. As opposed to over here, if we take the energy of our products, which is a lower number than the reactants, which is a higher number, when we take our smaller number minus the larger number, product minus reactants, it will yield us a negative value for delta H. So again, that's how we know negative value exothermic for delta H, positive value endothermic. Any questions on that there? Okay, so let's continue on, I think. We also talked about the idea of sort of heat and energy flowing from the hotter temperature to the cooler temperature. So if we have sort of two waters there on opposite sides of a little wall, and we got 90 degrees and 10 degrees, the heat is really going to flow from our warmer side to our cooler side there. And we'll start to see more energy being picked up on the cooler side. The result of that is the cooler water's temperature should rise as it picks up that energy. And as the hotter waters gives away that energy, the temperature should start to drop, and they will probably meet maybe somewhere in the middle of their two temperatures, the average. About 50 degrees in this particular case. So our warmer guy gets cooler, cooler guy gets hotter in terms of this temperature. Remember, temperature is sort of a reflection of what we look at in terms of energy being absorbed or released. Somebody releases energy, we see the temperature start to come down, right, for that object. Somebody is gaining energy, we will see it kind of the energy and the temperature sort of increasing for that object. The other really important thing that we talked about, which is important in this chapter, is the idea of sort of that perfect exchange of energy. So if somebody gives away a certain amount of somebody that will gain the exact same amount of energy. The only difference is for one of them, it's exothermic, and for the other, it's endothermic. The number would be the same. So if we had somebody giving away 50 kilojoules of energy, it would be negative 50 kilojoules of energy for that guy because it's releasing it. If say the surroundings is picking that up, it would be positive 50 kilojoules of energy as it picks up the same amount of energy. Any questions on that there? Let's talk a little bit more about enthalpy, which is our delta H, and it's again a very common way that we sort of experience energy in chemical reactions, as we mentioned maybe last time at the end, a lot of times in equations, they'll just write the chemical equation out, and at the end they'll go, hey, the delta H for this reaction is this number. Maybe it's a positive number, maybe it's a negative number, depending on it's exothermic or endothermic. You could actually calculate the delta H of a reaction by taking the products minus the reactants. So if you're just given a actual equation by itself, like say you had 2A plus 4B goes to 2C, you could go to a table, like a delta H of F table. The F here means formation, and sometimes it's just a table. And you could look up values like the delta H value for A, maybe it's 4 kilojoules. The delta H value for B, maybe it's 2 kilojoules. Delta H value for C, we'll go with 6 kilojoules. So there is a table and a lot of books and ways where you can look up these delta H values for everything. There's a couple of things that you always want to make sure if you ever go to a table like that or need to use a table like that. First off, you want to make sure obviously you get whatever you're looking for in terms of what the substance is, but just as important, you want to make sure that you actually find it on the table in the correct state. So if the thing's a gas, you want to find the gas value. If the thing's a liquid, you want to find the liquid value. If it's aqueous, you want to find the aqueous value and so forth. There will be different delta H values in these tables for different states of things. So you just don't want to kind of find the first sort of formula that you're looking for and hope it's the right one. You also got to double check and make sure it's the right state. Delta H of formation is basically what the energy demand for each of these guys to be formed from their sort of elements. And things that are in their natural state, uncombined, like H2O2, things like that, they will have delta H values always of 0. So anything that's basically uncombined by itself will always have a value of 0. So sometimes in tables they leave those off because they think, well, it's supposed to be 0. So sometimes it will be zeros. So how we go about this is, the other important thing is when we do this type of calculation, we also do need to take the coefficient into account. So if I were to do this calculation and calculate the delta H of the reaction, I would start with my products. My products has a coefficient of 2 for C. So I would actually take 2 times the value of C I find in my table, which is 6 kilojoules. And that pretty much takes care of all my products. Then subtract it and basically do the same thing. I have 2 of A, so I have 2 times the value of A from the table. And I also have another reactant here, which is B, plus 4 times the value of B from the table. All my reactants. So these are all my products. These are all my reactants. And basically in this example here, we would just add those together. So we got a little bit of 12 minus, we got there 8 and 8, 16, I think. So 16 in this case. So we'll end up with a minus 4 kilojoules in this made up example. The number tells us a couple of things. Would this reaction be exothermic or endothermic in this case? It would be exothermic, as it is a negative value. So we see a negative value for delta H will tell us that overall this reaction is releasing energy as it happens. So it's important if you do calculate this, and this would be a situation where pretty much all you're given is the equation. So that's all you're given, just a chemical equation. And they're like, what is the delta H for this reaction? That is always a situation where you go find the table, look up all the values, take the coefficients into account, add up all the products contribution, subtract it from all of the reactants contribution. Any question on that there? Yeah. Is what I wrote in, I'm sorry. That was just an example of a reaction. So it just happened, this is a made up reaction with letters. So why don't we do one here, or a couple here with some real stuff, and you'll give it a try. So let me write a couple examples here. Let's say we had, let's say we had N2 plus, which is a gas, plus H2 makes NH3. Do a little balancing like his chemistry class here. There we go. And we want to find the delta H of this reaction. And let's do CH4 plus O2, CO2 plus some water here. And a little bit of balancing here would be good. So that's a 2. Put 2 there, 4. Or 1 and 2, so we're good. And our delta H of this reaction. So we're going to give you some values that obviously you would find in a table. So some of these delta H values from a table. So let's go with H2 is 0 kilojoules. O2 is 0 kilojoules. N2, 0 kilojoules. Let's do CH4. Minus 74.6 kilojoules. Let's do CO2. Minus 393.5 kilojoules. H2O. Minus 187.6 kilojoules. I think that's everybody. Oop. CO2, water. All right, so take a couple minutes here. So for each of these reactions, calculate the delta H like I just showed you a second ago. You want to add all the products minus the reactants. You also want to make sure you take the coefficients into account there and multiply each one by that. Yes. What is, I'm sorry? I am missing NH3. Thank you. That would probably be helpful. So NH3, let's go with minus 46.3. Thank you. Now I think you should have everything there. Okay, let's take a look, see how you're doing. So we'll start the first one. So once again, if this is a situation, like pretty much this is the question, looks just like that. You're given the equation, what is delta H? We're always going to do our delta H of our reaction, going to be delta H of our products. Once again, problem, you would go find the table pretty much to find all that information I wrote in the middle there and find it by the correct state. So we'll start with the first one. We're going to take our products. So on our product side, we have 2 of the NH3. So we do need to multiply 2 times the value for NH3 that we have in the table, which looks like it's right there, minus 46.3 kilojoules. We are then going to subtract it from our reactants. So in this case, the coefficient is 1. You really don't need to put the 1 there, or really the rest of it, but it will be 0 kilojoules because that is the value. And for our H2, there's a 3, so 3 times 0 kilojoules in this case. So basically, it's all about their products there. And if we do that, we will end up with 46.3 times 2, negative 92.6 kilojoules in this case. First off, any question on that calculation there? You should show it, yeah. This is exothermic or endothermic, this reaction? It is exothermic. We know that, again, simply by the negative sign that we got here. So the negative is what tells us that. If we're going to do our second one here, we're going to do the same thing. We're going to start with the product. So in this case, we got a couple of products. So the CO2 is 1. You really don't need to put the 1 there, but if you want to, you can. We'll go with negative 393.5 for the CO2. We are then going to add it to our other product, which in this case is 2 waters. So we do need to take 2 times the value of water, which would be minus 187.6 kilojoules. So that's basically all of the product's contribution here in terms of energy. We're now going to do the same thing for our reactants, figure out their contribution. We have 1 times the CH4 value, which would be minus 74.6. Once again, you don't need to put the 1 there unless you want to. And then our O2 is also 1 times 0, basically. And this would basically be all of our contributions from our products in this case. So minus 393.5 plus 2 times negative 187.6 minus negative 74.6 looks like. Looks like we end up with something like minus 694.1 kilojoules in this case. Once again, we do see a negative value there for the energy, which means that this is exothermic. This is pretty much what happens when you light your Bunsen burner. So obviously you're familiar with it, gives off heat and energy. You do that. It's an exothermic sort of process. Any questions on how you would calculate those things there? Clearly the delta H table would be given to you, obviously. Any questions on that? Now, in this case, we didn't get any positive values, right? But if we did the reverse of the first reaction, what would happen? In terms of energy, it would be exactly the same, except these would be your products, these would be your reactants, and it would become positive 92 if you did the reverse reaction, where NH3 went to N2 and H2. So again, there's that conservation of energy. A process takes the same amount of energy, no matter which way you're kind of doing it. It's either you're giving it off or you're absorbing it. Any questions on that? Yeah. Talked about that. So the next thing we're going to talk about is actually calculating what's known as specific heat. And specific heat is a way that we can simply calculate the energy of a reaction. And as you'll do on Wednesday's lab, I think, basically you could do this very simply with like 2 styrofoam cups, basically, and a thermometer, basically, in it. And really, by just following the change in temperature of the solution or water, you can really figure out how much energy is either being given off by a particular reaction or absorbed by a reaction. The actual specific heat capacity is basically the amount of energy that's required to raise 1 gram of a substance by 1 degree Celsius. That's almost the identical definition of like what a calorie is, except that it is the energy needed to raise 1 gram of water by 1 degree Celsius. There is a formula to calculate specific heat, and personally I roll with this one myself here, which is Q is equal to ms delta T. Q is the heat or energy. It usually has units of joules or calories. Usually has just 1 unit. M is mass, which usually has units of grams. The S is the specific heat capacity, which is this guy right here. And that is joules per gram per degree Celsius or calories per gram per degree Celsius. Now, some books and some people will use SH instead for specific heat capacity. Some people will use C as well. So you'll sometimes see C used or SH used in place of S. I personally just use S, but again, some books use C or SH in place of for specific heat capacity. And the most important one in this one is actually our delta T, which is our final temperature minus our initial temperature, and that is in degrees Celsius. So this is one of the few chemistry equations or formulas where you actually leave the temperature in Celsius. And that's because most of the time in chemistry, the tables that we use will have the specific heat capacity in degrees Celsius. So everything cancels out correctly. Physics likes to use Kelvin. So you'll sometimes if you take physics and do this sort of calculation, you'll have it in Kelvin. But actually here we usually will leave it in degrees Celsius because the specific heat capacities we look up are usually in degrees Celsius as well. So everything cancels out correctly. Now, important difference is these two guys, and sometimes very often sort of messed up. Q has only 1 unit, either it's joules or calories. The specific heat capacity has all 3 units. So it's very common. People always kind of reverse those 2 things. So if it's Q, it should have just 1 unit. And again, if it's specific heat capacity, it should have 3. Again, this is a formula where if we calculate Q and we end up with a negative number, it's going to be an exothermic process, energy being given off. And this is a deal where if we calculate Q, it's positive, it will be endothermic and energy would be absorbed in this case. Now, when we look at this formula, pretty much Q is going to be positive or negative. M is positive. S is a positive value. So the delta T is really the most important thing here because it is the change in temperature that's really going to give you either the negative or positive value when you do the calculation. So sometimes people are taught just that, take the difference of the temperature, it doesn't really matter. So you definitely want to always do final minus initial. That will work out the positive or negative value for you when you calculate Q. If something, again, releases energy, what that's going to mean is their final temperature will be less than their initial temperature. So when you subtract it, you'll get a negative number. And if somebody absorbs energy, their final temperature will be higher than their initial temperature, and that will give you a positive number. So really important to always do final minus initial, always get the correct sign when you're using this equation. Because when you calculate Q, you do want to know if it's exothermic or endothermic a lot of times. And if you just sort of ignore the sign, you might not know. This is the specific heat of water. It's not negative, so it's just from PowerPoint. And that is something that they want you to know. That's the specific heat of liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. So those are two values that you should know. And those are the conversion factor to go from calories to joules. So 1 calorie again is 4.184 joules. So that's basically the specific heat of water. So if you remember that conversion, you should always have the specific heat of water given to you in your head. It will not always be given to you. Also, it's really important, as we'll see on the table next, when you go to the table to look up values for a specific heat capacity, other than this one, which you should know. It does change based on the state. So if we're dealing with liquid water like we are here, it's 4.184. If we're dealing with ice or steam, which is basically water in different states, it's more like 2 joules per gram per degree Celsius. So it is different based on the state. So you always want to make sure, again, that you hit the right state. If I have a really large value, or I won't say really large, if I have a large value for specific heat capacity, does it take more or less energy to change the temperature by 1 degree Celsius? If I have a large value for specific heat capacity, it means that you would need more energy, right, to change 1 gram of that substance by 1 degree Celsius. As if you had something that was a smaller specific heat capacity, you would need less energy to change 1 gram of that substance by 1 degree Celsius. Liquid water has a specifically high specific heat capacity. That's why people are concerned when the ocean water changes by just like a small little degree, right? You go like, that doesn't seem like a lot, but it takes a lot of energy. You think about ocean water and how many grams of water there is. It takes a lot of energy just to move the temperature by that little bit, right? So that's why it's always of a concern, you know, in terms of temperature growing in the water, even though it may sound to you like a very small number. So here's a table of specific heat capacities. Again, that 4.184 is a number you should know, along with the 1 calorie per gram per degree Celsius. But underneath it, you can see ice and steam are about 2. Iron is about 0.45. Gold is 0.1. So you may have to reference a table to find specific heat capacities. Just make sure that you obviously get it in the correct state, much like any table that you ever use in chemistry. You always want to make sure it's the correct state. You do not. So the one that you need to memorize is this one, yeah? And the 1 calorie per gram per degree Celsius, yeah? Other questions? The others would obviously be provided for you, yeah? All right, so let's try one out here. Determine the amount of energy as heat that's required to change the temperature of 10 grams of aluminum from 25 to 58, specific heat capacity 0.89. Give the answer both in joules and calories. Take a minute or two, see what you come up with. Take a look here. So obviously we're dealing with specific heat. So we could start with our equation. Q is equal to ms delta T. We obviously pull out here our 10 grams. We have the specific heat capacity that was given to us at 0.89 joules per gram per degree Celsius. We have our initial temperature at 25 degrees Celsius, and our final temperature here at 58 degrees Celsius. And once again, we're looking for the heat or energy, which is Q in this case. So we basically got everything we need to plug in there. So our Q would equal our 10 times our specific heat capacity of 0.89 joules per gram per degree Celsius. Once again, we want to do final minus initial, so that's going to give us 58 minus 25 degrees Celsius. In terms of units, our grams will cancel, our degrees Celsius will cancel, leaves us just joules left over, which is a unit of energy. And if we pop that into our calculator, we end up with a number. End up with 293.7 joules at this point. First off, any question on the calculation part of it? Sig Fig wise, since we're chemists, I suppose we should do that. That is going to be a 33 on the subtraction there, I think. That is going to then be 2 Sig Figs. That has 2 Sig Figs. This has 3 Sig Figs. So my answer really should have 2 Sig Figs when it's all said and done. So that would take us to like a 290 joules. We also wanted to then convert that into calories. So once again, 1 calorie is 4.184 joules. So we'll go with our 290 joules. We'll use that Sig Fig number, I guess, 4.184 joules per calorie. Joules will cancel, dividing it divided by, if I could get the number, 4.184. Gonna give us about a 69 calories. If you just went with that number, I think you got 71 or 70 or something like that, so if you used a rounded number, probably in this case you would use a rounded number, since this was sort of really the conclusion of one of the answers, right? Was the end of it there was 290, so probably round at that point. Any questions on that there? This process endothermic or exothermic? It is endothermic. Our Q value is positive. We also see that our temperature started at 25, right, and ended at 58. So as it gained the energy, the reflection of that was the temperature went up. So that all makes sense. Yeah. Any questions on that? All right, let's try maybe another one here. 294 joules of heat is transferred to 10 grams sample of silver at 25 degrees Celsius. What would be the final temperature of the silver if the specific heat capacity of silver is 0.24? We could do the final temperature in Celsius, degrees Celsius. Let's take a look to see how we're doing. So once again, obviously we are using our specific heat equation. So we can pull out our information again. This case, this is Q. Once again, this is going to be Q. It has only 1 unit. Yeah, so remember that's the one that has the 1 unit. So that's going to be 294 joules. We have our mass, which is 10 grams. We have the initial temperature of 25 degrees Celsius, and we are looking for the final temperature here. And once again, our specific heat capacity is 0.24 grams per degree Celsius. So we have everything we could kind of put into our equation here. So we got 294 joules would equal our mass of 10 grams times our specific heat capacity of 0.24 joules per gram per degree Celsius. Remember that when we do the change in temperature, it is final temperature, which is what we're looking for, minus our initial, which is 25 degrees Celsius at this point. We want to make sure that we do solve this mathematically correct would be good. That means originally here we are going to first divide these guys, right? So basically we're going to divide both of these guys to the other side. I guess I should make my arrow go that way. So if we do that first, we'll take 294 divided by 10 and divided by 0.24. That gets us a 122.5. And when we do that, that is degrees Celsius, as the grams here will cancel. When we divide, the joules will cancel on the other side when we take it to the other side. That will equal our final minus 25 degrees Celsius. So obviously at this point, if you see this, you should now know we're going to add that to the other side. So now we're going to take this basically and add it to the other side, which would be plus a 25. That gives us a final temperature there of about 147.5 degrees Celsius. We weren't looking at any Sig Figs. That was obviously what you would get on your calculator. First off, though, before we get there, any questions on the calculation part of it? All right, so let's talk a little Sig Figs of what we did. So obviously we divided first in this process here. So these two guys were basically divided to the other side, which means we should look at Sig Figs. And the Sig Figs we should end up with at this point is how many? 2, right? Which actually would take us to here, right? That's kind of where we should be. But now when we add this number to the other side, we should look at decimal places, right? And the smallest number of decimal places is this guy that has none, which means we really should take the answer to a whole number, which means if we went off with this number, 148 degrees Celsius would most likely be the final answer. Now, if you strictly did some Sig Fig over here, you would have ended up with a $1.20, right? Plus 25 would get you 145 on the back end there. I would probably be okay with it if you did it that way. But in this case, since all this is sort of one calculation, really, it's not multiple calculations in order to do multiple processes. To me, I'll divide like I did, and I actually would roll with this whole number at this point, since I'm just going to be adding that at the end and then sort of clean it up, you know, to the 148. But again, if you strictly did it to 120 at this point, you know, in this situation, you might not want to go rounding yet, but keep track of where it should be. So at the end, you know where you should kind of end up with in terms of your answer. Any questions on that there? This also makes sense if we just think about what is happening in this problem. The Q value was 294 and it was positive, which means that this process is endothermic or exothermic? Endothermic, which means as this process continues, would we expect the temperature to go up or down? Should go up, and it did, right? It started at 25, ended at 148. So it definitely gained all that energy. The result of that is we see the temperature increase, which again makes sense. I say that because in some cases people try to do too much at once in the calculation part, and they end up like maybe subtracting when they should be adding and adding when they should be subtracting. So it's a good idea to think about, you know, does your answer make sense at the end? Any questions on that one? So another very common sort of specific heat situation that we come across is the idea of heat being transferred really from one object to the next. And in this formula here, the C is specific heat capacity. So that's the same as S in this equation here. But what happens in a situation where we have something that is, again, higher in temperature than something else, and we kind of put them together, we are going to get that heat transfer from the hotter situation to the colder situation. And for example, like the experiment you're going to do on Wednesday, and a very common one is, let's say we had some water, and we could do these things, like I said, in a sort of a coffee cup, has a calorimeter, is very well insulated, it works really well. But let's just say we had some water here that's had an initial temperature of like 25 degrees Celsius. Let's just say we had like 75 grams of it. And we know the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius. Now, if I take a piece of metal, kind of like what you're going to do on Wednesday, and let's just say we had, you know, 60 grams of a metal, and let's say the initial temperature of the metal was like 95 degrees Celsius. When I take this metal and I throw it into my beaker of water here, when you do it, hopefully you won't throw it, but you put the metal into the water. Now I have my water to my metal that's swimming in the water here. What's going to happen to the temperature of the water? Will it go up or will it go down? The water's temperature should go up, right? Because the metal is much hotter. So it's transferring all that energy from the metal to the water. As the water picks up that energy, we see the temperature of the water start to go up, and the temperature of the metal should then start to go down as it's exothermic, giving off that energy. So let's just say the final temperature of the water was like 28 degrees Celsius. Now, with my metal sitting in there, what would be the final temperature of my metal in this case? What happens when you put something like in a cup of water? Eventually, if you come back to it, it will be the same temperature as the water is sitting in, right? It will come to equilibrate itself to basically the same temperature. So in this situation, when you take this really hot metal, it's going to release all that energy. The water will gain some energy, and eventually the metal will actually come to rest at the same temperature as the water is at the end. So it would also, in this example, be 28 degrees Celsius, as that is the final temperature to water. So this process, which is known as calorimetry, and like I said, could be done very simply like you'll do on Wednesday with 2 coffee cups, styrofoam coffee cups, a lid, and a thermometer. You basically can follow the temperature change that occurs with water, because we know all about water, specific heat capacity and the temperature change. As long as you know the mass of the water you start with, you could figure out how much energy that the water has absorbed in this particular case from the metal. And the relationship, though, that's important here is this: the energy of the water, or the heat of the water, would be negative the heat of the metal. So what does that mean? It means that they are numerically equal to each other, but the sign should be different. So if I find my water gains energy, right? My Q value for water should be positive or negative, which means then the metal would be negative. That same number would just be negative for the metal because it's releasing the energy and it's exothermic. The water would be endothermic. Opposite would be true if you had hot water, right? And put a colder piece of metal in there, right? If you put a colder piece of metal in the hot water, what happens? The cold piece of metal warms up, right? The hot water cools down. So it's the opposite process that could occur. So you can't go in both directions depending on what's happening here. So what we can do in a situation like this is, because we know everything about water, we could basically calculate the heat that the water is going to, in this example, absorb by just doing our normal calculation of 75 grams, our specific heat capacity of liquid water, and our final minus initial, which would be 28 minus 25 degrees Celsius. And what we would see in this case, 75 times 4.184 times 28 minus 25, in my made up example, 941.4 joules of energy would be gained by the water. And again, it's positive in this case, like we would expect, because it's absorbing all that energy. We can now use this relationship, which is really the equation on the next page, this relationship right here, that the negative energy of that should be how much energy the metal released in this case. So all the energy that was required to raise the temperature of the water had to come from the metal. So it has to basically release that exact same amount of energy than the water absorbed. So it would be negative 941.4 joules, if I ignore Sig Figs for this example here. And what that will now allow us to do is actually calculate the specific heat capacity of this metal if we weren't sure what it was. And if we did Q for the metal, it would be MS delta T. Specific heat capacity would be Q of the metal divided by M delta T. Taking our numbers, minus 941.4 joules, our mass, which is 60 in this case, and our change in temperature. What should the change in temperature be for the metal in this case? Final would be 28 minus initial, which would be 95. And that's really important because that's going to give me what type of number? A negative number. So again, here we want to make sure that we do 28 minus 95. That is going to give us a negative number. Along with this negative number, we'll turn our specific heat capacity into a positive number, which is what it should be. So again, it's really important to make sure that you do that final minus initial, whatever we get when we do that. Any questions on that calculation? So this is a very common sort of process that we use for reactions to figure out how much energy is either being absorbed or released in a reaction. And as I mentioned a couple of times, you could do it with 2 styrofoam cups. I think they use 3 here. Again, a lid and a thermometer. And this is what is known as calorimetry, where basically you're following the change that occurs in water. We can even do this for chemical reactions that don't technically have water, or it is water. Any solution that's aqueous, solutions that come out of the bottles, they're typically water-based. So even though they're technically not water, we could still treat them as the majority of it is water and still do this type of calculation to figure out the energy that's being absorbed or released, even though, say, you use hydrochloric acid versus, say, water in the reaction. And when we do this at constant pressure, when we calculate Q, that is the same thing as the delta H of the reaction. So this is a super simple way that you could just take coffee cups. You could pour 2 reactants together that are aqueous, let it do its thing, and follow the change in the temperature. And basically, by just using a thermometer, you could calculate the delta H, or the enthalpy change for that particular reaction that's occurring. It's a super, super common sort of thing. We do a version of it on Wednesday. We do this, not really a reaction per se. We're just taking like a solid piece of metal and dumping it in. When you go to 1A, you'll do actual reactions where you mix them together in the coffee cups. And basically, because they're basically all water-based, we could just basically treat them as water, and it makes the calculations really easily. And it's a very convenient and easy way to figure out the change in enthalpy or energy that's occurring in a particular reaction. Any questions on that? All right, so why don't you try one here? This is basically exactly what we just described. See what you come up with. We'll give you the density of water, which you should know, by the way, which is 1 gram per milliliter. All right, we got 110 gram sample of metal at 55 degrees, 55.5. It raises 150 milliliters of water from 23 to 25.5. What is the specific heat capacity of the metal in this case? This is pretty much the exact calculation you will do on Wednesday's lab. Take a look. So this again is pretty much what we were just talking about. We got some water. We have a hotter piece of metal. We're going to drop it in there. And again, it's going to basically transfer its energy to the water because the metal is hotter. So we have our specific heat equation that we can actually use for both things, the water and the metal. So if we sort of add up the stuff that we got going on here for our metal, we got a mass that is 110 grams. We also have an initial temperature here of 55.5 degrees Celsius. For our water, we have a volume that's 150 milliliters. And we do have the density, right? So density is mass divided by volume, which means mass is volume times density. That would be basically 1 times 150 milliliters. And that converts to 150 grams of water by multiplying 1 times 150. Yeah. So you do want to make sure you get that to the right units, which are grams in this case. And again, we're basically going to times this by 150 milliliters. We have the initial temperature of our water, which was 23 degrees Celsius. We have the final temperature, which was 25.5 degrees Celsius. We always have the specific heat capacity, which is 4.184 joules per gram per degree Celsius. We want to determine what the specific heat capacity of the metal is. The other piece of information that we have, which is not explicitly said, is the final temperature of the metal in this case should be what number? Should be the exact same final temperature as the water. So it's sitting in there. So once it goes for a swim, it's going to come to the same temperature as the water around it. So although it doesn't explicitly say it, we do have this number here, 25.5. If we look at really all the information that we have, we pretty much have everything that we need for the water to calculate how much energy is going to be absorbed in this case. So we'll start with the water in this case, and we'll do Q of our water would be the mass of the water, which we converted to grams, not milliliters, by using the density. Our specific heat capacity there of our liquid water, and our final temperature 25.5 minus our initial, which is 23 degrees Celsius. Getting an answer here gets us 150 times 4.184 times 25.5 minus 23. Going to give us on our calculator about a 1569 joules. If we were shooting for Sig Figs, which we might want to do in this case at this point, what should the Sig Figs be? When we subtract here, we get 2.5, right? Which is 2 significant figures, 4 significant figures, 4 significant figures. Means technically that number should actually be 1600 joules, right? Which would be that number right there. Yeah. Any questions on that there? This is a positive number, which does make sense because the water, again, is gaining all that energy as the metal goes for a swim, right? So we should expect it to be a positive number. Now that we have that, we could use our relationship that Q of the water is equal to minus Q of the metal. That means Q of the metal in this case should actually be negative 1600 joules if we use our rounded number here. Again, it should be the exact same number, but the sign is different because the metal is releasing the energy. So it should be a negative value for the metal, which would be exothermic for the metal. Any questions on that there? That's an important thing. Bless you. That's an important thing because now for the metal, we have Q, we have M, and we have the delta T, which means for the metal, we can now solve for the specific heat capacity. So Q of the metal will equal ms delta T. The S would equal to Q of the metal divided by M and delta T, dividing both of these guys to the other side. Yeah. Putting in our numbers here, we'll go with minus 1600 joules divided by our mass, which was 110. And our change in temperature, which again should be in this case, final minus initial. And that would get us our 25.5 minus 55.5 degrees Celsius. That once again is going to give us a negative value that we need to cancel out the other negative that is there so that we end up with a positive specific heat capacity. And if we did that there, 16, 110 and 25.5 minus 55.5. We end up with 0.48. The units here are joules per gram per degree Celsius, as none of the units cancel. None of these cancel. Sig Fig wise, technically this would still be our 2 Sig Figs. That would be 4 Sig Figs. And when we subtract here, that's like 30, I think, 0.0, which would be 3 Sig Figs. So we end up with 2 Sig Figs here. Any questions on that calculation? That's a very common calculation with specific heat where we basically just follow the change in the temperature of the water to help us understand what is happening in terms of exothermic and endothermic. In this particular case, if you rolled with the non-rounded number, you would end up with the same number at the end. With rounding, you should end up, I think you get 0.475 or something like that, right? Or so you'd end up with 0.48 as well. Any questions on specific heat or how to calculate these things? Again, this is pretty much identical to the lab on Wednesday. So that's how you do the calculation on Wednesday, in case you're curious. Any questions on any of that there? All right, I think we will lay it up there.